So let's say for reasons known to themselves, they choose to ask you to evaluate this integral. Well, you can try this using integration by substitution as well as by parts, but you're going to fail dismally. And the word dismally means you fail without any chance of success. So the correct integration technique we must use is trigonometric substitution, because this integral is in the form a squared minus x squared. And of course, in this case, our a is going to be 5, because 5 squared is 25. And every time we have this form, we have to make a substitution of x to be a sine theta. So that's what we must do in this case. We are changing from the variable x to the variable theta. So here we let x to be a, and then we say sine theta there. And next, we need to differentiate x with respect to theta. So we say the derivative of x will just be 5 cos theta d theta there. And since we are moving from x to theta, it makes sense for us to change our limits of integration and express them in terms of theta. So how will they look like? Well, for the lower limit, that's when x is 0, and this is equal to 5 sine theta. Then we divide both sides by 5. So we find that the sine of theta is 0, and the arcsine of 0 will also be 0. So this is our lower limit. Now, what about for the upper limit? Well, the value of x is 5, and this is equal to 5 sine theta. Do you see that? This is where it's coming from. And so dividing both sides by 5, we find that the sine of theta is 1, and the arcsine of 1 will just be 90 degrees, pi over 2 radians. Okay, fine. So now we are ready to come and express this integral in terms of theta now. So we say it's the integral from 0 all the way to 90 degrees. But when we see x, we now put 5 sine theta, and then we square this. And when we see dx, we simply put 5 cos theta, and then we say d theta like that. And then we say, well, 5 sine theta, which is all squared, it's just going to be 25 sine squared theta. And then we times this by 5 cosine theta d theta there. And then from this point, we can see that, well, inside the square root, we have a common factor, which is 25. And if we take it out, from the first term, we are left with 1. From the second term, with sine squared theta. And of course, we still have 5 cosine theta d theta there. Then from this point, we say, well, every time we see 1 minus sine squared theta, we actually see cos squared theta. And this one, of course, we still write it exactly as it is. Then we say the square root of 25, it's just going to give us a solid 5. And the square root of cos squared theta, it's the absolute value of cos theta, but then we are going to take positive cosine. Why do we take positive cosine? Well, it's because we are integrating from 0 to 90 degrees. And this is in the first quadrant. And in the first quadrant, that is where cosine is positive. So you can write the absolute value, and then on the next step, omit the absolute value. But I'm just going to omit it from the get-go. So what? Oh, we still have our limits of integration there. So we have the integral from 0 to pi over 2. Then we say 5 times 5, it's 25. And since 25 is a constant, I take it outside the integral sign. And so I'm left with the integral of cos squared theta d theta. Now, this is where the problem arises. If you choose to convert cos squared theta and write it as 1 minus sine squared theta, you are not solving anything, but instead, you are creating more problems for yourself. You're actually digging yourself a grave. So what is the solution then? Well, we are going to change cos squared theta and express it in terms of another identity. So every time you see cos squared theta, you need to know that you actually see 1 plus cosine 2 theta. But there's a half in front of this bracket. And then you say d theta there. But if it was sine squared theta, you're going to have 1 minus cos 2 theta. So now you've learned 2 new identities. Well, that's fine. So this 1/2 is a constant. We take it outside the integral sign. And so we get 25 over 2 times the integral of 1 plus cos 2 theta, which is evaluated from 0 to pi over 2. Then we say, well, the antiderivative of 1, it's just going to be theta. The antiderivative of cos 2 theta, well, it's a composite function. So we say, what is the antiderivative of the outside? Well, antiderivative of cosine, it's sine. But the chain rule says we keep the inside function as it is, and then we divide by the derivative of the inside function. And then we say, well, this is evaluated from 0 to pi over 2 radians. And then we distribute this 25 over 2. So when we do, we get 25 over 2 theta plus 25 over 4 sine 2 theta. Yes, because sine 2 theta over 2 is the same as half sine 2 theta. And of course, we still say we evaluate this from 0 to 90 degrees. Then from this point, we apply the fundamental theorem of calculus. So we substitute the upper limit. And by the way, there is no need to substitute the lower limit because everything will die when you do. So when you substitute the upper limit, you have 25 over 2 times pi over 2. And here you have 25 over 4. Then you say sine 2 into pi over 2. Well, for this one, you say 2 by 2 is 4. So you get 25 pi over 4. And you come here and say, well, 2 multiplied by pi over 2 is pi. And the sine of pi, the sine of 180 degrees, it's 0. It's at the x-intercept. And since the sine of 180 degrees is 0, then it means this whole thing is going to die. So this implies the final answer will just be 25 pi over 4. Or if you like, of course, you can say it's 25 over 4 pi, whichever way you like. But both of them are equally correct. So yes, that is how you evaluate this integral by using trigonometric substitution. Well, thank you so much for watching. I really believe and hope this video helps a lot.